Hi, I'm Pedro Rodriguez, and today I'll talk to you about our EACL 2023 paper, Fighting Fire with Fire, Assessing the Validity of Text-to-Video Retrieval Benchmarks. First, an outline. I'll give an overview of text-to-video retrieval evaluation. Particularly, I'll talk about how this task is actually formulated, as well as the datasets and benchmarks that are used to measure this task. Then I'll talk about problems affecting the validity of current TVR benchmarks, which we evaluate by collecting a new dataset, which we call the FIRE dataset. And then using that, we analyze model differences. In particular, we analyze how model metrics differ when we use the original dataset versus the original added to the FIRE dataset as well. And then we talk about what future evaluations should do to fix the shortcomings that we talk about in this work. So first, an overview. So what are the inputs to this task? A query, which is a textual search query. For example, a black and white horse runs around. A video collection, which is what we want to search over. These get fed into a model, which is supposed to output a ranked list of videos from 1 to n that are relevant to this search query. For evaluation, we count the number of gold videos in the top K, and then we can compute various metrics like precision and recall. So if we assume that video 1 is the one and only correct video for this situation, precision is 33% and recall is 100%. But where do these videos, queries, and labels come from? Predominantly video captioning datasets. So datasets that were not originally intended for text-to-video retrieval. And that introduces several problems. So let's talk about the datasets first. So in this paper, we study MSR VTT and MSVD, commonly used datasets. The videos come from clips from the web or on YouTube. And the captions are written by annotators. So they were told, please caption this video and write several captions. And the relevance labels don't exist in this dataset, but they're rather constructed from it. So we treat the captions as search queries, for example, horse riding in grass, and all these other captions were written for one particular video. In this case, the video to the right. The candidates are any video across the entire dataset. And relevance labels for each query video pair are decided by saying that the associated video, the video that was captioned by this caption, is a positive, and all other videos, even if they seem to match, are negatives. The problem with this labeling scheme might be apparent that it introduces false negatives and label errors, and the reason is that captions can be quite general. For example, a horse riding in the grass could match that video from the last slide, but it could also match other videos in the dataset. So there's many unannotated videos that actually do match. So for example, if I have this caption, lady and her dogs, and I toss this into clip for clip and get predictions, the top 3 videos are arguably correct, but they're all negatives in this case. So we call this as like having a fire in the kitchen of evaluation. So our data set's called FIRE for false implicit relevance labels. Here are more examples. So we fed these inputs and annotated the predictions of clip for clip, teach text, which is shown as experts here, and SSB. And here what we're basically showing is under the original evaluation and under the FIRE evaluation, whether a video is marked as relevant or irrelevant. So for example, if I have a test caption, cartoon girl is talking, arguably video 1 and video 3 should be positives, but in the original dataset, the top prediction from this model is not correct. But in our annotated dataset, our annotators marked this as correct. And then you see the original label down below. Please note that in our evaluations, we count things as correct if the video was an original positive or it was a positive in our data set. We don't toss out the original data. So what questions did we try and set out on this work? First, how many false positives are there? And how do false negatives influence the benchmark metrics that are used for this task? So in our experiments for building the FIRE dataset, for MSR VTT and MSVD, we grabbed 3 recent state-of-the-art models, clip for clip, teach text, and SSB, and got all the queries in the dataset, got the top 10 predictions for the test and val data, sent those for annotation. What did we tell the annotators? Our goal was to preserve the original relevant semantics of the original task. In that task, the captions by definition must match the video, otherwise they would be inaccurate captions. So in our task, we told raters to label relevant if all the video components match and irrelevant otherwise. We see generally very good agreement, and what is not unexpected is that the ratio of relevant to irrelevant labels was pretty skewed towards many irrelevant compared to relevant, and that's just because if you grab the top 10 predictions, most of them are probably not going to be relevant for either because the model's wrong or just because there's not many videos that match any particular caption. So what did we do with this data? So we took this data and we calculated benchmark metrics with only the original positives. So this is basically the standard evaluation setup. And then we recomputed them with the original positives and the fire positives that we collected, the top 10 predictions from each of these models across both data sets. And then we recompute. And the big question is, do the metrics agree? Well, the short answer is that they don't, which is why we have this paper. So I'm going to show this table. You can gloss over it for a second. In this table, corrected N means at least one correct video is in the top 10, and AP is average precision. So in the left column, what we're showing is the metric computed with fire annotations, so the original plus ours. Then the next column over is showing the metric computed without fire annotation. So this is the standard setup. This is what you would see in current published literature. And on the right, we're showing the delta between these two. And what you can see is that, for example, clip for clip gains 25 percentage points absolute on correct.1. In other words, if you compute the metrics for clip, you get 42% with the current standard setup. But then if you manually, yourself, go and annotate all the predictions that clip has, what you'll see is something closer to 67%. So the metric is not telling the truth in that case. And this leads these benchmarks to understate model quality. Curiously, we didn't see much improvement for teach text and SSB. Intuitively speaking, from inspecting the results, I think the clip for clip predictions across the top 10 are a bit more sensical, and teach text and SSB seem to be more random, which would explain this. The other thing I want to point out is if we looked at clip for clip correct at 10, or recall at 10, this benchmark looks like it's approaching saturation with 95% with the fire annotations compared to 80% without. So considering, depending on what your task is, you might consider that this is not enough headroom to focus on this task for this particular metric. So what were the other questions that we wanted to answer? Do short general captions have more false positives? And why did clip gain so much in this case? So our basic hypothesis is that shorter captions are by definition more general, and therefore, because they are more general, they will match more videos. If we look at the MSVD captions just qualitatively, we can see this play out. A man, a baby, a woman, camp, these are all pretty general concepts because there's not much to express in the caption compared to long captions that can be extremely specific. So shorter captions will tend to match more videos. We saw this borne out in the data. This plot is showing the number of positive videos and the caption length in words. So for example, if we look on the far right, where the number of positive videos is quite high, there are comparatively more captions that have short caption length. And this totally makes sense and supports that hypothesis. The other thing that we looked at was for every example, if we compared two models head to head, in this case, clip for clip and teach text, there are 4 possible outcomes. They could both get an example correct, only clip for clip could get it correct, or teach text could get it correct, or neither model could get it correct. What this is showing is, for example, if we look at all the captions between 30 and 40 length, which is where the peak of this distribution of the histogram is, showing the density of the data, we can see that there are many examples where neither model gets it correct when you use the original annotations. But when we move to the fire annotations, that's where clip makes large gains because there are not as many cases where clip doesn't get this correct. So this basically agrees with the previous data that we had that where the extra positives are coming from are the short captions, and the short captions is where clip seems to do pretty well. But this doesn't explain why. We did a few other experiments, but in short, it's difficult to explain why a model does well in a particular case. We can have certain hypotheses and put forth data that maybe suggests that this is the answer, and we have that in our paper, but there's no clear indicator it's because clip for clip does X thing better. So, what are our conclusions? First, text to video retrieval benchmarks substantially understate current model quality. And for some benchmarks, they might currently be saturated. TVR should also have better benchmarks. And we talk about this more in our paper, but they should have benchmarks that better preserve construct validity, i.e., they should represent the real world use case. Doing search by treating captions as search queries and random web videos as, say, personal video collections isn't representative of me searching for videos on my iPhone, for example. Second, benchmarks should have better internal validity by addressing this challenge of false positives, which is very common in retrieval settings. Currently, benchmarks are understating model quality. When I see a metric, it's not reflecting how good the model actually is on that metric, and that's something that we don't want for our evaluations. Thanks for listening, and see you at EACL in Croatia.